The original Nobel winning equation, the Black-Scholes PDE, and the formula assumes that there is no dividend during the life of the option or the derivative. But in practice, considering dividend yield is important. In this video, we'll present the modification of this Black-Scholes-Merton formula for pricing of European call option and put option. So, the main observation is that the dividend yield Q causes the stock price to reduce on the ex-dividend dates by the amount of the dividend payment. The payment of this dividend yield at rate Q therefore causes the growth rate in the stock price to be less than it would otherwise be by the amount Q. With this observation, we can see that the following two distributions are the same. One, the stock starts at the price ST and provides a dividend yield at rate Q is the same as the stock starts as price S times e to the power of this quantity and provide no dividend. So as a rule, the valuing of European option can be modified in this way. Just we replace S of t by the quantity ST times e to the power of minus Q times t minus t and value the option as though the stock price has no dividend. So in the original Black-Scholes formula, we will replace S of t by ST times this quantity. That is the modification. Hence, the pricing formula for the Black-Scholes equation will follow the following. The price of the call option, you see in place of ST we have this quantity. Again, in place of ST we have additional quantity here. For the detailed explanation, look at the previous consecutive videos. So this is only the modification. So the corresponding differential equation which is related to this solution is the following differential equation, which considers the payment of the dividend with yield Q. Remember that the original Black-Scholes differential equation is just we multiply this part by R, but this one is R minus Q will be the modification of the new. In the same way, the price process of risk neutral process of the stock price will be given by this stochastic differential equation. And once we solve this stochastic differential equation, we will get the closed price with this modification. The remaining things are all the same. We already showed the code in the previous video. Then you can modify the code by adding one additional parameter, which is dividend yield Q. So it will be reflected here in the equation like this one. The other thing will be all the same. So we encourage our video observers to review and look at the previous discussion. So this is an example with the dividend yield 2% with the same parameter as a previous example. So the price of the call option to be equal to this one, and this is the price of the put option. We can also do for the historical data, for example, by importing the Apple price, the closed price of Apple for 2 years historical data, and by simulating, right? So by simulating the next 1 year, for example, by considering just a yield. Of course, we don't know the yield, but we can take just a number for the purpose of demonstration. For example, here just everything is not exactly correct, but we calculate the return, the volatility, and take number of simulation, for example, just 5 or 50, the time to maturity, number of steps, and the initial price for the next 1 year. And then this is possible paths, and take the average of the possible paths. Okay, then this is just the plot of the possible paths. You see, by considering the dividend yield, the price compared to the price without the dividend is decreasing, as you can see that. And this is a plot of the average simulation or the expected price. Let us take here strike price 230 and apply the call option by calling the Black-Scholes analytical solution. Also calculate the put option by inserting all the parameters. In the same way we did in the previous video, we can also calculate the prices through time from 0 to capital T using for loop, and we can form a table. That means a table, this is the first column is time step, and this one is the price, then the call and the put option. So therefore the main thing is here we can modify the original Black-Scholes differential equation by assuming by inserting a new parameter. Thank you very much.